Thank you, Hassam. Everybody here in the back of the room okay? Good. So I really wish Craig and I would have talked a little bit more. We talk every week, and I really wish we would have looked at our slides together. But I'm going to take maybe a higher level view. I'm not a cement chemist, so I think I'm going to try to make it maybe somewhat more relatable for the average person. So I'd like to talk about carbon uptake, just what it is, that we're recognizing it more and more. Briefly go over the chemistry. Craig gave you really in-depth chemistry. I'm going to give you like the ABCs, the really, again, high-level view of it, and what it contributes to carbon neutrality. The importance of the baseline for measurement and reporting. You heard Craig saying that we're doing all this work to really dial that in and get it accurate. And we want to be able to quantify carbon uptake at the project level, and also, I guess you could say, at the country level. There's current data gaps. Again, Craig is filling in some of those. There's opportunities for research and data. So that's what we're just going to touch on. There's an activity at NIST, Low Carbon Cements and Concretes Consortium. I'll just tell you briefly about that. They will be meeting here, I think, Tuesday afternoon. I think they're still looking for more participation, if anybody's interested in the topic. And then I'll kind of frame it up with PCA's policy priorities, what we're working toward, what we'd like to see. So there are some key resources. Craig touched on them. The idea of carbonation occurring in concrete has really been known about for a long time. But it's probably 2005 by this researcher Lagerblad with the Swedish Cement and Concrete Research Institute, who put the idea of carbonation in terms of life cycle. So what's the CO2 uptake of concrete during its life cycle, however it's exposed? You come to 2017 and you've got that British standard EN 16757 on PCRs and EPDs. They have that Annex BB that is about the guidance on calculating CO2 uptake, right? You come in this 2021 period and you have the IVL Report B 2309, which is called the IVL Swedish Environmental Research Institute report. Again, the title, CO2 uptake in cement-containing products. And then the big one here of everything is this assessment report by the IPCC. I got it on the next slide. I'll tell you a little bit more about it. But this is a comprehensive assessment report on climate change. So it's not just cement, it's not concrete, it's everything. Everything that we do, everything that contributes to carbonation, carbon dioxide in the atmosphere, that's what that covers. So this one is the 6th time this report was put together. The good thing for us is they recognize carbonation. They say, CO2 emissions from carbonates and cement production are something on the order of 4% worldwide. So this is, again, everything that we do. Where does cement fit in? You often hear, I work for the Cement Association. I know our manufacturers hear about it too. Some are in the room. Is cement the bad guy? Can we have a world without cement and concrete? So we got a target on us, and this is sort of putting what we're responsible for into context. 4% is a relatively low amount, but of course we could do better. And then the other thing that this report says is they recognize that the CO2 uptake that is due to carbonation will offset, like you saw Craig report on, a significant portion of the emissions that come from manufacturing cement. So it's that idea that we can pull it back out of the air. It's just going to happen. We don't really have a choice. So again, PCA is the Portland Cement Association. We represent U.S. cement manufacturers. We have a counterpart, GCCA, the Global Cement and Concrete Association. They represent manufacturers of cement throughout the world. We both put out a roadmap to carbon neutrality or to net zero. PCA's was published October 21. We took this approach, what we called a linked value chain of the 5 Cs. So we make clinker, we produce cement from that, we make concrete out of it, we build with it, so construction, and then carbonation is the last C in the 5 Cs. And that's the idea of, again, concrete is a CO2 sink. So we have it going from 2030 up to 2050. We have the amount of carbonation that's going to be taken up by concrete that's out there increasing. It's on the order of 10% per year, 9, 10, something in that range for us. GCCA took a little bit of a different approach getting to net zero, and you can see it's very dynamic. They show you 2020 to 2050. The CO2 sink, recarbonation, sometimes it's called that, they have it at about 6% for every year. Again, it depends on the mix of everything else that you're doing, but something on the order of 6 to 10% might be what you'd expect to see. This is where I wish Craig and I, we had dinner last night together, we never talked about slides, but when you manufacture cement and then what happens with carbon uptake, so manufacture, you saw all the really complex chemical equations that Craig showed. I'm going to dumb it down because that's more what I can understand. Calcium carbonate, limestone, right, the primary ingredient. We add heat to it to break the chemical bonds so we can get at calcium oxide, lime, the backbone of cement. But when we do that, we drive off CO2. Everybody, I think, is familiar with that in our industry at this point. Hydration, that CaO, again, very dumbed down, not all the complex equations. There's a lot of different equations occur and sometimes in stages, but we hydrate that and we get calcium hydroxide. Again, here's the simplified part of it, that calcium hydroxide and other phases will combine with CO2 to go back to limestone or calcium carbonate. So it's that idea of a cycle and water. You can show it on a micro scale kind of here, so calcium carbonate, carbonate to calcium oxide to calcium hydroxide, production, hydration, carbonation. They're constantly looping like that. If you look at more of like a macro scale on concrete now, we make cement, the CO2 gets driven off. This is a picture right out of Annex BB. So we're driving off CO2, we're producing concrete with it, that structure is gonna pull CO2 into it. And again, what happens when we demolish that structure at the end of life, crush up the aggregate, whatever. We got this cycle. So always this idea of a cycle. When I first started, there was a nice little brochure at PCA that talked about the lime cycle. This is really the lime cycle, if you will. So the baseline for carbonation then is clinker production. Producing clinker generates CO2. And it's roughly, almost as much CO2 as it is clinker. Fuel emissions, whatever we're doing to heat that limestone up, we don't get those back. So whatever we can do to keep the fuel use low, that's good. We won't have to worry about recapturing that somehow because we can't do that. You saw Craig talk about this, the calcination emissions, which are about 60% of the CO2 emissions at a cement plant. That's the theoretical maximum uptake. And I say theoretical because you saw Craig say, we expect even with block, which is really porous and open structure, they're only looking at maybe 75% that they can get back. Some of that unhydrated cement isn't even available to take up CO2. So still, over geologic time, 60% of the emissions that we needed to get to cement, to make and build all the things that we like building, we can get 60% of those back. So this roadmap, again, the idea that PCA looked at this and tried to compartmentalize everything into one of those C's, there's multiple levers that we have to reduce CO2 emissions, and we really want to use all of them. So it's things like reducing the clinker factor. So for every ton of cement that we make, it contains right now, currently on average, about 0.91 tons of clinker. So there's 9% other stuff in there. By 2050, we're hoping that we can get that clinker factor down to 0.75. So we'd be putting in 25% other materials. This is a big deal because we still need the cement to gain strength. We still need it to be durable over a long time. So even targeting that at 25 years from now, that's still a really aggressive target, but we think we can get there. We can use decarbonated raw feed to reduce our CO2 emissions. So if we're not driving off CO2 when we manufacture cement, that'll help us because we're starting at a lower baseline. We can use lower clinkering temperatures. Again, here, the fuel emissions aren't offset. You're going to see sort of innovative and new fuels being used. If we can get to lower temperature to manufacture, that helps us too. And then this idea of promoting recognition of carbon uptake. So it's an all of the above approach. All of it's important. I'm shouting out MIT's work here, and probably Bensu's going to talk a little bit more about this. Two more speakers, I believe. But PCA helps through the Concrete Sustainability Hub at MIT. Hassam and Bensu, of course, work there. We help support their work. One of the things that they did was develop a really nice little calculator. Online, you can go to MIT's CS Hub. You can download this in Excel spreadsheet format. It's really nice, and it takes into account some of those key references and others, the Annex BB, the IVL report, Lagerblad. It's got data that it's drawing from all of those. And it says, just fill in these little boxes for us here. We got drop downs for you. What's the time? What's the life cycle? How long is that structure expected to live? Geometric and locational characteristics. How much volume of concrete? What's the surface area? How is it exposed? Is it in a wet or a dry condition, inside or outside, above or below ground? Those sort of things. So you've got all these factors built in based on a lot of that research, a lot of these key reports for the last 20 years or so. You've got cement, you've got mixed design. So we can just consider that like by strength, because as you saw Craig talk about, your more porous materials, your lower strength materials generally, those allow carbon dioxide to work their way from the outside in. So that's what this calculator does. It pulls all that together, and we know cement and concrete practices can vary by country. So it doesn't matter if you put in a blended cement or if you put in a fly ash or a slag at the ready mix plant. We've got the characteristics all kind of spelled out here. You can pick what you want from the drop down. So then this green box actually calculates what your use phase of the carbon dioxide is. So that's as the concrete's exposed. And we can see for this particular thing, it was 195 kilograms of CO2. The second part of the calculator is what do we do for the end of life? So end of life storage affects carbonation. How we store it matters. What's the size of the aggregate pile? How big across the bottom, the top, how tall it is? What kind of grading? If we keep it uniform grading sizes in that aggregate pile, air can work its way in better. So we actually want that kind of exposure. So again, the exposure conditions, we put all those into the drop-down boxes, and we get an end-of-life carbonation uptake here. So those two added together give us our CO2 offset or emissions. That's kind of a project-level idea. At a country level, this is where that IVL report comes in. Again, PCA helped support the work that resulted in this document. So the Swedish Research Institute, again, May 21, they come up with 3 methodologies. They call them Tier 1, 2, and 3. Tier 1, simplified. Tiers 2 and 3, you need more effort. You need more data. You need better analysis, higher level analysis, better tools, more specificity. What's really the numbers for you and your country and where you are? So if we're just going to look at Tier 1, which was I told Hassam we could have time to go through, that's your first estimate. It's a conservative estimate for the use stage, end-of-life stage, and secondary use. The uptake values are related to the calcination emissions. Again, this is why it's so important. We have to understand how much cement is produced. We have to understand what the emissions from that are. That's our baseline. Just like Craig talked about the background interference, we have to know what we're starting from. So it is the production in a country minus the export plus the import. How much concrete are we building in that country? That's what we're trying to get at with that aspect. And then the CO2 uptake for existing structures on a national basis. So we use an annual clinker consumption data piece for this. We take a 20-year average. We even out the highs and the lows. We smooth it out. How much cement is being used in that country and then how much are we going to be able to get back in terms of what happens with the carbonation of that concrete that's made with it. So from that other BB annex report, the maximum theoretical CO2 uptake that they've established there is a 0.49 kilograms of CO2 per kilograms of cement. So the use stage says we're going to get 20% uptake of the calcination emissions. The end of life and secondary get 2% and 1%, so 3% of the calcination emissions. So if we had a country using 10 million metric tons of Portland cement annually, and that emissions factor that we just covered, that country is contributing, again, globally, 4.9 million metric tons of CO2. This is where that 4% idea comes in. We're adding all of those up. So the use stage, if we take 20% of this, we get 980,000 kilograms. End-of-life secondary use, we're going to get another 147,000. So 10 million metric tons of cement will absorb 980, 147, 1.13 million metric tons, kind of on a national scale, you could think of this. So about 11.3% of the calcination emissions over the life of that concrete for that amount of cement. Just again, kind of a ballpark calculation here, a starting point, if you will. I borrowed one of Craig's slides because it's nice. They're doing research that's better quantifying the rate and total uptake of the CO2 into their products. You saw that, the progression, the pink is not carbonated. When it starts to get clear, it's carbonated. CO2 is working its way in from the outside. That kind of research could benefit other kinds of concrete products. So this is qualitative. We're not able to calculate a CO2 number from this, but it is showing us what's happening. And then we're going to figure out how to quantify it. That's where NIST is really coming in and helping. So again, this group called LCCCC, Low Carbon Cements and Concrete Consortium, started in 2022. Their charge, if you will, is to develop traceable and accurate measurement techniques. So standardized techniques to measure carbon and carbonate in cement-based materials. You saw Craig talk about it's kind of difficult. Are we getting accurate numbers when we're doing this? So they want to create this information to inform the guides and the standards and the specs. They're doing that through 4 work groups: quantifying carbonates, specifications, carbon accounting, novel materials, products, processes. So that's really the work that is going on right now to help us get to a better understanding of what we can measure. And you heard Craig talk about TGA, thermogravimetric analysis, where we grind up a sample, we burn it, it drives off different species at different temperatures, so we know exactly how much of it is in there. The phenolphthalein that test, that we saw, just a visual, qualitative test with the pink color or not. There's a lot of other things that NIST is looking at. Can we use IR, infrared analysis, or mass spectrometry, or X-ray diffraction? So they want to have a lot of different test methods available so we can accurately quantify how much carbon dioxide is being pulled into our materials. How much of a sample size do we need? Concrete has coarse aggregate in it. Mortar has just fine aggregate. All those background interferences that Craig talked about, we have to be able to pull that out, and we have to get accurate CO2 measurements. So wrapping up, how PCA is involved and why we're involved. Again, our manufacturers are responsible for CO2 generation. So we want recognition and validation for what actually happens with carbon uptake. Are there established or accepted methods for calculating it and for quantifying it? Life cycle consideration. We, as the cement industry, as the concrete industry, we have environmental product declarations that put us at pretty high embodied carbon and pretty high embodied energy materials. But that's only a piece of the story. It's the beginning. If you don't look at the whole life cycle, then you're really not maybe making your most sustainable choices, because that's where this is heading. EPDs are going to be used to inform what people are building with. And the EPA has a big grant program out right now to put money into the system so that we create more EPDs. Again, EPDs are an important piece of information. How we use them, life cycle assessment, that's really good. That'll inform sustainable procurement policy. If we really want to have an impact in driving down the CO2 of what we're building with, you got to look at the whole picture. And then more research on the life cycle carbonation and the benefits of concrete materials, including the end-of-life treatment. So with that, I would say, I hope it wasn't too repetitive from Craig's. Thanks.